Hello, friends. Welcome to our session and discussion about the sensitive ground fault detection methods, types, its settings, and importantly, the deep knowledge behind the settings. Uh, in previous sessions, in 5 sessions, we discussed about the 3I0 stage with the measuring of cosine and sine methods for measuring method. And in this session, we are just getting a review on some of what we have discussed, and we will cover some points on direction determination delay, V threshold, and 3I0 threshold. For the direction determination for this block, we have discussed before that which system we should use the method of measuring cosine or measuring sine method in previous sessions. We have covered that if we have arc separation coil system, arc separation coil grounded system, then we select the cosine method and we do not tilt the symmetrical angle. And also for the resistive grounded system, we said that we use cosine method and we just a little bit tilt it by minus 45 degree. We tilt the symmetrical axis because mostly the current which is in the system is more inductive because the impedance of the system during the resonant conditions try to neutralize, and here the capacitive part of the current and resistive part of the current try to compensate each other, and the remaining important part of the current is the inductive part of the current. And if the current is inductive, so the majority of current will occur in this direction, so we tilt our symmetrical axis by minus 45 degrees so that the part which is perpendicular to this symmetrical axis becomes more achievable. And in the systems which is not grounded and isolated system, we said that we use the sine method and we do not tilt our symmetrical axis. This is the forward and this side is the reverse direction. So during the setting, first we select the method for the measuring of the direction, whether sine or cosine, based on our system grounding, and the phi correction, that is the tilt angle of the symmetrical axis, which we discussed, and minimum polarization, zero sequence current for direction determination. That is minimum polarization, zero sequence current for the direction determination, that is these lines. It means how much current we limit that current, that beyond that amount of the current, our system will start determining the direction, whether in forward or in reverse direction. So this amount is, by default, it is 0.03 amperes. But for each system, how much amount we should take, we are discussing right now. Here you can see that if we have a system which is a type of arc separation coil system grounded or Peterson coil grounded system, then our core balance transformer is installed, and we expect that, for example, at the amount of the current which is flowing in the line and during the fault, what amount of the current will be in our secondary of the core balance transformer. That amount of the current, that is expected measuring current during the fault, divide by 2. That amount we select for the minimum polarization current. This amount of the current, which we select. And if we have our system isolated system, the same, we are finding that we expect that what amount of the current will flow during the fault, the residual current of course, that amount we divide by 2. That is the minimum polarization current for direction determination setting. And for the system, if it is not that is for the system which is not grounded, and for the system which is resistive grounded. For the resistive grounded, we find the minimum fault current which flows into our secondary of core balance transformer. That amount of the current, we find the minimum amount of the current during the fault, and that minimum amount of the current during the fault is our setting for the minimum polarization current for direction determination. Another setting which also we have discussed, that is the alpha 1 reduction direction area and alpha 2 reduction direction area. That is these two angles, alpha 1 and alpha 2. These angles determines the angle of two axes, axis of alpha 2, axis of alpha 1. For the direction determination limitation, we limit the parts because in some of the systems, maybe in high inductive systems and fault fluctuations, maybe our current 3I0 maybe in parallel to the axis of symmetry, and this may guide our system to a misoperation forward or reverse direction. To prevent that misoperation and misguide of the direction determination, we apply the direction limitation reduction area. It means we reduce the area of the direction by these two axes, so that the direction of, for example, this current should be undetermined. Where this current, we don't want this current. This current is not in some systems, it is not in forward direction even. The default value for these two values of alpha 1 and alpha 2 is 2 degrees in the Siemens relays. But if our system has more misoperations, so we can change it, we can increase or reduce it. Now these settings are applied to the block of direction determination block. It's applied to this block. Now this block has another inputs, and we are discussing each by each. And that is the direction determination delay. Sometimes in the systems during the initial start of the fault, we have transient currents, and mostly that transient condition will misguide our system, and it will misguide that okay, the direction is reversed. For example, here it's one of the graph after the fault, it means during the fault. So during the fault, this is the transient of our system. If this current flow, even though this is whatever the picture I have taken is the picture for the phase current, but suppose this type of the graph is the graph of the residual current and the neutral current which we have in our system. If it be like this, if we don't give any time delay for the direction determination, in the initial time it will misguide our system because the current will flow in the reverse, and the relay will be misguided that the fault is beyond. It means the reverse. Actually, it's not the reverse. The fault is not in the reverse direction, but our relay will be misguided, and that current is the initial time. At the initial time, that current is in reverse direction, in backward direction. So the system will introduce it as a reverse fault. That's why we give some amount of the delay. It's around 50 milliseconds. By default, it's 0, but around 50 milliseconds. We give a time delay, or less than this amount, because 50 is even more. We give some very, very low time for direction determination delay, because whenever the V0 is determined and it passes the threshold, it is around 30 volts. This amount is around 30 volts, and it depends on our system, of course. That setting we should give according to our system. When it passes the threshold, then some amount of the delay will be applied, and that signal, now the V0, is supplied to the direction determination.